I will encourage them to do that as we go here.
And they will sustain Q&A really well in the seminar.
Good.
We haven't had any downtime.
No, I print out the list of questions every day in case there's a pause, but no. It's like being the Maytag repairman on this end.
Yeah, we just sit here, oh, guess they don't need us, click and clack, except for comic relief. All right, I'm letting the children in. You ready? Here they come. They're out there in Zoom land. Woo!
Hey, John.
Greetings, Earthlings. Hey, that's appropriate for today.
Yeah.
Shin, it's your day.
It's Space Day. All right, welcome. It's click and clack again for, unfortunately, sadly, penultimate class.
It is.
Boo. But on an up note, we really brought in a star, beaming in from Central Arkansas University and deep work with honors. We bring to you, and I'm going to use his Twitter handle because yes, Professor Lusk, I've been spying on you. Professor Jeremy Space Trash Lusk. Let's give him that big honors college welcome. So, Professor Lusk is a very interesting case because he actually was in the Honors College, which is a fine honors college at the University of Central Arkansas, before he traveled to Norman, Oklahoma, to work as an astrophysicist in their Department of Physics, where he earned his PhD. And I love this story, and I'm hoping some of you follow Professor Lusk in this. He went back to his alma mater, is paying it back, teaching amazing courses in physics and astrophysics, and also working closely with the Honors College at the University of Central Arkansas. Now, he has a lengthy publication list, which I, of course, found because I am the CIA. It's all topics way above this medievalist's head, however. So I'm going to let him talk a little bit about his research area. But I certainly can tell you that Professor Lusk is an award-winning teacher who came super highly recommended to us by the Honors College at UCA. And finally, considering that his Twitter handle is Space Trash, and I didn't plan this at all, we kind of ended our conversation weirdly yesterday talking about throwing trash into space. So now I give you Dr. Jeremy Space Trash. Take it away.
Hi, folks. It is very, very good to see you all. I'm very honored to be able to take part in this May intercession class. I get to step outside my comfort zone a little bit and go back to my roots as an honors kid from UCA and get to talk about things like ethics. So I'm excited to be here. To talk a little bit about what I do, I study supernovae. So I study the huge explosions that kind of end the lives of very massive stars. And my research group and I at UCA are working on figuring out just how bright those things are, which is a tricky problem because to know how bright something is in space, you need to know how bright it looks, but also how far away it is. And that second part is really hard. So we are working on that and involving some interesting kind of computational research as well. So my background is kind of in astronomy and supernovae and computers. So ethics of space exploration is something that I'm excited to talk about, but it's also kind of outside what I usually do, which is fun. It's fun to get outside your comfort zone. So I will go ahead and take over here and I will start sharing my screen. And I'm also getting over a cold. So if I disappear for a second, it's to spare you from coughs and nose blowing, because that's not polite. Okay, so hopefully everybody can see this and hear. Hang on, let me change one thing real quick. Let me do this and that and that and that. Okay, there we go. So this picture is very special. This is a picture of the kind of last view that we had of the JWST, the James Webb Space Telescope, as it was released from its launch vehicle and started its months-long journey to its position at a Lagrange point in space, where it can start to view deep space using infrared light. Now, this picture is also special because for me, this happened Christmas morning. It was a pretty amazing thing to watch, this launch, because the JWST took 18 years to complete, billions of dollars, lots of delays, lots of patience from the astronomy community to get this thing off the ground and into space. And it was very special because I got to watch this while I was cuddled in bed next to my 6-year-old, holding his little pin of the James Webb Space Telescope. And I bring this up because space is very near and dear to my heart. I got really interested in astronomy and astrophysics, even though I didn't quite know what that was, at a pretty young age. I grew up watching documentaries on the Discovery Channel through our pirate cable box and reading every book I could get my hands on about space and what was out there and where the universe came from. And I grew up knowing names like Jocelyn Bell Burnell and Vera Rubin and Carl Sagan. These were kind of my heroes coming up. And it was really special to be able to share that with my kid. And so to start us off, I want to ask some silly questions. All right, silly question number 1. What is space? So feel free to chime in at any point during the talk in the chat with answers to questions. None of these are rhetorical, and I will keep an eye on that as we go here. But I think like a decent working definition for us today of what space is to make a programming joke, not Earth. So this is where I get to make terrible jokes, and there's nothing you can do about it. So the little exclamation point there in programming talk is sort of a not symbol. There we go. Thank you, Tasia. You got it. So everything that's not here on Earth, space station, the moon, other planets, the sun, other stars, other galaxies, the whole universe, everything that's outside our little blue ball here is a decent thing to call space. But a slightly more difficult question, and Cassidy, thank you for setting me up here, where is space? And this brings us to an interesting question. So Cassidy said outside our atmosphere. And that's actually kind of tricky to define. So this next picture shows the Space Shuttle Endeavour. And it's a picture taken from the International Space Station. These are both spacecraft that are in orbit around Earth. And in the background, lit by the sun that has yet to rise over the limb of the Earth, you can see several different layers of our atmosphere. So the blue stuff here is our mesosphere. This is sort of the layer of the Earth where all the weather lives. Directly behind the shuttle, in that blue area, is the mesosphere. The atmospheric layer that's kind of white near the nose of the shuttle is the stratosphere. And that sort of orange stripe is the Earth's troposphere. So all of these layers of the Earth here, and I misspoke a second ago, the troposphere down there at the bottom is where most of our weather lives. These layers don't have clear boundaries, and you can kind of get a sense of that in this picture. As you look up to the upper right, you can see that mesosphere kind of just fades out. There's no clear edge to it. In fact, the International Space Station itself, and this is a question that I love to ask in class. So in class, when I'm teaching, I'm either sitting in Conway teaching a class, or I'm sitting here at my house in Little Rock because of a pandemic teaching a class. But regardless, I assume most of my students are in Central Arkansas. And so I ask a question when I teach about the orbital dynamics around the Earth. What's closer, Memphis or the International Space Station? And it turns out that the International Space Station's actually closer if it's directly overhead. You don't have to actually go up all that far to get to space. And in fact, the orbit of the International Space Station is low enough that it's not fully outside the atmosphere. And every 6 months or so, because of the atmospheric drag on the solar panels and the structure of the space station, you got to give it a little boost to keep its orbit up. And so this just sort of reinforces this idea that there's not a very clear line between Earth and space. And so we have to come up with mostly artificial lines between Earth and space. So here's a diagram that kind of shows the first 100 kilometers of the Earth's atmosphere with some sort of landmarks along the way. Off to the left there, we have a couple of graphs of pressure and temperature. As the pressure is high, and high in this case means to the right, as the pressure is high, you can think about that as being a nice thick atmosphere. And you can see that in the first 10 kilometers, the pressure drops dramatically, right? Mount Everest is about 10 kilometers high. And so as you get up to the top of Mount Everest, you are entering what's called the death zone, where there's not enough air for you to live. Commercial airliners fly just above that. High-speed, high-performance aircraft like the Concorde or the SR-71 Blackbird fly much, much higher than that. And by the time you get up to those heights, you don't have much atmosphere left, but you are still very much within Earth's atmosphere. You're not at zero yet. Things like weather balloons will make it up to about 40 kilometers. And where we define the edge of space varies. So the FAI, which is sort of it is a body that is located in Switzerland, and it's sort of the record-keeping organization for the aerospace industry. They're the ones who kind of keep records of the highest, the fastest, the most. They define the edge of space to be at 100 kilometers, what's called the Kármán line. So that's up here at 100 kilometers. The United States Air Force has traditionally defined it to be 80 kilometers. You get your astronaut wings in the US Air Force if you go over 80. So Ethan's got a question in the chat. Why does the temperature fluctuate like that as you go up? You would have guessed it would have changed in a more uniform way. Yes, but it gets kind of hard to talk about temperature. It looks an awful lot like up here at the stratopause. It's nice and warm, like it is down at the surface. And that's technically correct, but in a way that only physicists would appreciate. It is technically nice and warm, although there's so little air, you still freeze to death and die. The air that is there, the molecules that are there, are zipping around quite quickly, and that's kind of how we define temperature. So that's caused by heating from if I get my brain set up right to think about the layers of the atmosphere, I think that temperature inversion that happens there near the stratopause is from deposition of like ultraviolet light into the atmosphere. It kind of absorbs that light and those molecules start zipping around quite quickly. I could be wrong about that though. But that's a great question. That's a good thing to notice. So you all have sharp eyes. I appreciate that. So as we go up to this 100-kilometer Kármán line, that's kind of the generally agreed upon line for the world. America uses 80, and that's just so that if you get your astronaut wings through the Air Force or through NASA, you both count at 80 kilometers. So anytime you hear about something happening at the edge of space, it seems like that would be happening up here between 80 and 100 kilometers. And that's not quite true. So if any of y'all remember back in 2012, an Austrian man named Felix Baumgartner went up in a very, very, very small capsule hanging underneath a very, very, very large balloon for a company that sells energy drinks, and then jumped off. He was performing a stunt called space diving. This was something that was researched by the Air Force back in the 50s as we were sort of preparing the space program to try and test environmental suits and also various methods of escape if you needed to jump out of a vehicle that was ascending into space. Those tests happened in the 50s, and then not a lot of people wanted to do that until this stunt. And Felix Baumgartner jumped out of this, and you can see in the previous slide here, at an altitude of about 39 kilometers back in 2012. And this is what it looked like. This is 5 seconds worth of footage from the capsule. So in 5 seconds, he went from standing on the platform, jumping off, to being completely invisible. On his way down, he broke the speed of sound with his head. And this was widely publicized as happening at the edge of space. You know, this guy jumped to Earth from the edge of space. But as we can see here, 40 kilometers is not exactly what we would call the edge of space these days. Now, his record was broken by Alan Eustace in 2014 at a height of 41 kilometers, and that currently stands as the highest space dive that has ever occurred. But I bring this up to introduce a few themes here. Themes of space, themes of private companies, and stunts. Because while this had some interesting implications for world records, this was questionably useful from a scientific research standpoint. An atmospheric parachute doesn't work at those altitudes. You have to just fall for a few minutes before there's enough air for you to open a parachute with. And we kind of already knew that. But nevertheless, this attracted a ton of attention. I don't know if any of y'all watched this happen in 2012, but it was very widely publicized when it occurred. And this brings us to a question, like, is this space exploration? Does this count as exploring space? I forgot the end of the story. Yeah, he was fine. Popped his parachute after about 4.5 minutes of free fall and then descended gracefully to the ground. He did great. So, and in fact, his sort of communications, the guy on the ground who was talking him through all of this was in fact this guy who did it in the 50s and 60s. So the only other person to do this crazy stunt was also the guy on the ground talking to him on the radio. So that was helpful. All right, so if this isn't space exploration, or even if it is, then that raises a question, right? How do we explore space? And for the purposes of this talk, I want to kind of break this up into two overlapping concepts, right? So Cassidy in the chat says, I wouldn't call this space exploration because his goal wasn't to experience and further understand space. And that's an excellent point to bring up. Yeah, I mean, this was higher than the last person who did it. But in the end, this didn't push the boundaries of our knowledge or our understanding very far. And it's questionable, you know, we can have an interesting discussion about whether you have to do that in order to explore space. And so I want to kind of conceptualize space exploration in two ways here. One is that we observe space without necessarily going to space. The other is that we go to space without necessarily observing it, and then there's all the mushy stuff in the middle where we both go and observe. So, you know, sometimes we do a little bit of both. So these are all icons And I'll put the citations for these icons in the notes that I send along for the YouTube channel. But these are some icons that just represent the various ways that we explore space. With ground-based optical telescopes, with fancy radio telescopes, with space-based observatories like the Hubble or the JWST, with autonomous rovers on the surfaces of other planets, with human spaceflight, and sometimes we just launch expensive cars into space. That I put on this edge because that seems to be a go there and not so much an observe. All right, so I have a question for y'all. In this picture that I'm showing you, how many individual stars can you see? So I want you to post some numbers in the chat. At least 10 from Dane. John says 0. Cade says 300. Kyle says 8. Josephine says billions. Love a good billions. At least 2, 1. Yeah. So this picture is very special. This is what's called the Hubble Ultra Deep Field. This is an area of the sky about the size of your thumbnail if you hold it out at arm's length. To a naked eye on the ground, and even to a good telescope, this patch of sky is pretty much empty. But when you dedicate hours and hours and hours of observational time with the Hubble Space Telescope, every orbit, taking a quick peek at the same part of the sky and just letting that exposure run for long periods of time. If you've ever played around with photography, if you've got very dim things you're trying to take pictures of, you need to take that picture for a long time to gather as much light as possible. And that's what this image is. This is the result of a very long exposure with the Hubble Space Telescope. By my count, there are 2 individual stars in this picture. Here's one here. You can pick them out because they've got these little spikes on them. So here's one here, and here's one hiding over here. Every other point of light that you see is another galaxy, equal to or larger than or a little bit smaller than our own. But every single dot of light is another galaxy. And this is incredible because, again, this is an otherwise empty patch of sky. Unless you look this hard, you don't see any of this. And what this reveals is something that's very important to keep in mind. Space is big, like really big. And when we kind of conceptualize the size of space, we have a really hard time because the numbers are literally astronomical. The distances are so large. And so what this means for us is that we need to think about this first mode of exploring space, observing. How do we observe space? If this is what we see when we look, what else can we do? Well, that's the problem. Because astronomers and astrophysicists, as we try to kind of understand and observe the universe, have very few tools available. If you think about a chemist, this is a picture of a graduate chemist at Lawrence Livermore National Laboratory doing some research on human hair. And what you can see in this picture is somebody who can bring to bear all of their human senses to research this question, right? The scientist can touch and look and hear and smell and maybe not taste in a chemistry lab, that might be a little bit questionable. But hey, geologists do it all the time. Don't let them tell you they don't. They lick rocks. So these sorts of sensory experiences are what we talk about when we talk about observing the universe. Dr. Mason's excellent talk about the philosophical foundation of STEM talked about the kind of ways that scientists understand the world around them, the natural world around them. And whether you're kind of a strict empiricist or like toward the end of the talk, you think about objective knowledge being achieved by the consensus of a diverse critical community, at some point in there, there's the act of observing, of measuring. And astronomers are constrained by the fact that space is so big. We can't go out and touch the stars. They're just too far away, and you would die. Hearing isn't very useful because there's no air up there to transmit sound, although there can be sound waves in space in places like galaxy clusters, which are very interesting to research. Smell, right? It turns out that space actually, at least the space around Earth, actually does have a very distinct smell that astronauts have reported these last 50 or so years. It kind of smells like sweet welding fumes, according to some astronauts. Taste. Don't lick stars. If you can bring a safety tip back from this talk, it's that you should not lick stars. Cassie says, I bet there was at least one geologist who licked moon rocks. Possibly. I don't know. And that kind of leaves us with sight. Can anybody think of an ethical problem that might raise if the only sense that you have to bring to bear is sight? If all you can do is use your sense of sight, are there any ethical questions or any ethical dilemmas that might bring about? Yeah, exactly. Right. So Dane, Cassie, Emily, you guys got it. Right. What happens if you do not have the sense of sight? And so let me modify my language a little bit here. Astronomers use light to study the universe, right? And while the first astronomical instruments were human eyes, sight is not a requirement to be an astronomer. And anyway, when it comes to light, right, humans are mostly blind anyway, right? So here's our picture. This was taken using visible light. But visible light is like a teeny tiny fraction of all the light that there is. And so most of this humans are blind to anyway. We can't see gamma rays or X-rays or ultraviolet light. We can't see infrared light or radio waves. And so as we conceptualize astronomy, we need to stop thinking about seeing and think more about detecting light. And so this light that we detect comes to us from space. And when it arrives at the Earth, lots of things happen, right? If we want to detect and analyze and observe this light, we can use our eyes, and we are limited to this little rainbow here. So let me kind of break this diagram down for you a little bit. Along the horizontal axis here, we have wavelength. You can think of this as color for visible light, but this is a measurement of how big the wave is, how long you have to, you can think about wavelength or frequency, they're interchangeable, but the wavelengths of visible light fall in this spectrum here. But if you go sort of shorter wavelength than violet, so ultraviolet, you end up not really being able to see that from the surface of the Earth, because the vertical axis here is showing you what's called atmospheric opacity. This is how transparent is Earth's pesky atmosphere to that kind of light. Now, what you can see here is that we are lucky. The kind of light that we can see makes it through the atmosphere. And of course, that's not luck, right? That's evolutionary adaptation. Our eyes are adapted to see the kind of light that is around because of the sun. So that stuff makes it through pretty effectively. Things get really messy as you go longer wavelength than red, called infrared. There are windows where that light can make it to the ground, but there are lots of blocked areas where, 80% of that kind of light never makes it to the ground. And as you go shorter wavelength to, say, ultraviolet light, that stuff mostly gets blocked by the atmosphere too. And that's good for us, right? UV light is super bad for humans. And so the fact that the atmosphere blocks most of that is great news for walking around. Kind of bad news if you're trying to do astronomy, because that light carries lots of information, just like the visible light that we see with our eyes. And the same story holds for X-rays and gamma rays and infrared. Now, we're also lucky that radio waves, our atmosphere is nice and transparent to a broad swath of radio waves. So that's nice. So we build these instruments in order to detect this light. This is a picture of some observatories on top of Mauna Kea in Hawaii. Off to the left is the Japanese Subaru telescope. In the middle is the Keck pair of telescopes. It's kind of a binocular setup. Off to the right is an infrared telescope looking through one of those little windows there to detect light from space. And these telescopes, you can think of them as light buckets. The reason why you want a big telescope is because very faint things, or things that are very far away, are hard to see. You need a big bucket to catch all that light that's coming to you, because it's very, very dim light that we're trying to detect from space. The objects themselves, of course, are phenomenally bright, but by the time that light gets to us, it has spread out so far that we only detect a tiny little piece of it. And we have to take that light and analyze it to understand what we're looking at. And so this brings us a set of challenges, right? If you want to observe space, you need a big telescope. You, of course, want to be looking at certain wavelengths of light that make it to your telescope if you're going to build it on the ground. And because you're on the ground, you got to worry about the bane of all astronomers, weather and clouds and rain. And even more than that, the atmosphere itself. Has anybody here ever looked at a star in the night sky and noticed it twinkling? And Josephine asks in the chat, aren't there a few animals that are capable of seeing infrared light? Absolutely. So the atmosphere blocks some of it, but I'm talking light from space. The infrared light that, say, a viper is adapted to detect is the kind of light that you and I are actually glowing with. So every object in the universe gives off light. We just don't notice the walls, the people, the rocks, the trees giving off light because they're not very hot. The wavelength of light that an object will give off changes with temperature. So something as hot as, say, the sun emits visible light. If you've ever seen something hot, so hot that it's glowing red, that is hot enough to give off visible light. But right before it glowed red, before it was giving off the kind of light you can see, it's giving off a ton of infrared light. So to skip back a couple of images here, you and I are emitting light, but that light is mostly in sort of the far infrared or the near infrared. So animals like vipers are adapted to detect that kind of light, because if you're a mouse skittering around on the forest floor in total darkness, You think you're good, only you yourself are a light bulb in infrared light. And so predators tend to adapt in those situations to be able to detect that kind of light. Emily asks, what about ultraviolet? That I'm less familiar with. I know there's actually a genetic mutation in humans that lets you see just a little bit further in the ultraviolet than most folks. I would imagine that would have something to do, because there's not a lot of it that gets emitted naturally by animals or plants. I would imagine that ultraviolet light might be an adaptation for like mating displays, or maybe there's some sort of like pigments in flowers that are especially reflective in ultraviolet. And so if you're a honeybee, or if you're what's the little tiny bird that flaps its wings real fast? Sorry, I'm on a lot of cold medicine. Hummingbird. There we go. If you're a hummingbird, that ultraviolet light might let you see, specific flowers better than other ones. So that I'm a lot less sure about. Okay, so to our telescope problem here, we have this problem of like, well, where are we going to put these things, right? We want them to be big. So here is sort of a big grand picture of some of the biggest existing and future telescopes. Down here at the bottom right, you can see the Hubble Space Telescope, which is up in space. The reason why you would want to put it up in space is because then you don't have that pesky atmosphere to deal with. I asked that question about stars twinkling. As that light tries to make its way through the atmosphere is acting like a very complicated lens that is twisting and distorting the light from the object you're trying to look at. To a human eye, that looks like twinkling. To a telescope, that can be a real problem. It can make it very hard to form sharp images. And so one solution is, we'll just get your telescope out of here. Get it up in space so there's no air to look through. There's no weather to cancel your observations. That's great, but as we'll learn later in the talk here, space is super hard and super expensive. So if you want a big telescope, you're going to have to build it on the ground. And these ground-based telescopes have evolved over time to be fantastically complicated machines that can correct for that atmospheric distortion as it happens, using lasers to create artificial stars in the sky, and then adjust their optics in order to adjust for the various twinkling and motions of the atmosphere above the telescope. It's incredible technology, and that's why a lot of these large telescopes are built out of many small segments of mirrors. All right, so Reed asks in the chat, do they look at anything specific with these giant ones? That European extremely large telescope seems like it would be unnecessarily big. So Reed, an astronomer will never say that a telescope is unnecessarily big. In fact, if you look at the background here, this circle in the background was a proposed but then canceled telescope called the OWL, the Overwhelmingly Large Telescope. Something I always tell my classes is that astronomers and physicists are terrible at naming things. We see a hole in space from which no light escapes. We call it a black hole. We see a red spot on the surface of Jupiter. We call it the Great Red Spot. We want to build an overwhelmingly large telescope. We call it the Overwhelmingly Large Telescope. We want to build a 30-meter wide telescope. We call it the 30-meter telescope. So these telescopes are large because they need to be able to see very dim things, right? If you want to be able to see very dim things, you need to be able to catch a lot of light. And so the bigger, the better. If you double the width of your telescope, you have quadrupled its light gathering power, right? And that's because the area of a circle, right, increases as the square of its radius. So twice as big is 4 times the area, and therefore 4 times the light gathering power. So even though it might look like this 30-meter telescope here is, it's bigger, but not wildly bigger than some of these other ones, like the Giant Magellan Telescope or the Hobby Eberly Telescope, captures sometimes orders of magnitude, powers of 10 more light. And that lets you look further back in time at dimmer objects to try and understand things like where the universe came from. So you got to build this big, giant telescope. You got to have nice weather. You want it to be preferably on a high mountain, because high mountains will get you up above a lot of the sort of most wiggly, complicated air. You want it to be nice and dry, so you're not looking through a lot of water vapor. And of course, you don't want a lot of light pollution around. You don't want a lot of, you don't want to put it in the middle of Los Angeles, for example, because there's just so much light coming from the city that it washes out the observations you're trying to make. And so what this means is that if you want to observe visible light from the ground, and you want to push the boundaries of what we're capable of as a species, you're going to need a big telescope. There's only a few places on Earth where a telescope like that could conceivably function. And this is a list of pretty much all of those. And what you'll notice is that these places are, generally speaking, pretty remote, very dry, very high up, right? Mauna Kea. These spots here are along the Chilean coast range, the mountains that separate the interior of Chile from the coast. They are some of the driest places on Earth at extraordinary altitude. Places like the Canary Islands, right? Places like the Himalayas, right? These places are ideal for this kind of project. And so what I want to talk about is the 30-meter telescope in particular, this one right here. So the 30-meter telescope has been in the works for decades now, and it is kind of a pair with the ELT, the Extremely Large Telescope. The ELT is going to be built and is currently being built on Cerro Amazones, which is in Chile, which is right here. That mountain is shorter now. We blasted the top off the mountain to make it nice and flat and start building this extremely large telescope on top of. But I want to focus on the 30-meter telescope because the location search for the 30-meter telescope was a complicated process. This is actually the list of sort of finalists. And then eventually, two places, Mauna Kea and Cerro Amazones, were selected as the sort of the finalists for these for this work. And the problem with that is you don't want both of your biggest telescopes in the same place. Specifically, you don't want them in the same hemisphere. Why not? Why can't you just put all your nice telescopes in the same spot?
You're going to limit your perspective. You're going to lose what you might gain through diversity of perspective.
Absolutely, right? You can't see the same parts of the sky in different hemispheres. And so if you're going to build a pair of extremely large telescopes, you really want them to be in two different hemispheres. The southern hemisphere and the northern hemisphere see different parts of the universe, right? Because it's easy to forget that we're all strapped to this spinning ball in space, and that changes our perspective, right? I, from Arkansas, cannot see two of the satellite galaxies that orbit the Milky Way, the large and small Magellanic Clouds. They're only visible from the southern hemisphere. So if you want to study those things, you got to go to the southern hemisphere. On the other hand, if you want to study the core of the galaxy, that's best visible from the northern hemisphere. So these kinds of things make a difference, the locations of your telescopes. All right, so this 30-meter telescope is sort of the next generation flagship telescope. It's going to be the highest ground-based priority in a document you read, the Astro 2020 report, which we'll talk about in a minute. The site was chosen to be Mauna Kea in 2009. In 2010, an environmental impact study was completed and approved. Conditional approval for the construction permits was granted in 2011. State Board of Land and Natural Resources approval was granted in 2013. Groundbreaking ceremony in 2014, which was interrupted by protests. Protests which continued into April of 2015. Protesters halted the construction by actually blockading the road that leads to the top of the Mauna, and 31 arrests were made at that location. After a few months, the Hawaii Supreme Court invalidated the construction permits, citing a lack of due process. The legal battle stretched on for years. Eventually, in July of 2019, the permits were approved. The public access to Mauna Kea was halted by order of the governor in order for construction trucks to start proceeding up the mountain to build the telescope. And protesters again gathered and blocked access to the mountain, shut down all operations of all 13 observatories on top of the Mauna. And Governor Ige declared an emergency, which allowed him to increase police presence at the protest and involve the National Guard. So why did this happen? We've been talking about space and cool science stuff, and all of a sudden there are protests blocking the construction of a telescope. To understand... Sorry, go ahead.
Oh, no, sorry. I don't know if your question was rhetorical. If you want to keep going, go ahead.
Nope, none of them are rhetorical. Go ahead.
Well, I was just really glad that you brought this up, because when you started talking about the Cerro Amazonas telescope, I thought, wow, did anybody consult with the local people, the local government? Did the local universities get to participate? And I know Mauna Kea is held as a sacred site to Native Hawaiians, and I doubt we went and asked them how they felt about the whole project. Or maybe we did. You can tell us about it.
Right. And so I actually looked into this because I had the same thought, right? Well, wait a minute. If we blew the top off of a mountain in Chile, didn't that also garner protests? I looked and admittedly did not look super deeply, but from what I can gather, the Atacama Desert is very dry. And that's not just now. It's been very dry for millions of years. So what I can surmise is that there isn't a cultural tradition in that part of Chile because people haven't lived there. It's been utterly inhospitable to human life. There have been a few archaeological discoveries made in valleys in the lowland parts of the coastal range, but most of the sort of archaeological and anthropological evidence from Chile comes from the coasts. And once you get up into the mountains, there's very little life to speak of. And so that's my assumption. I have not fully explored that. But for the subject of Mauna Kea, there is an absolutely rich tradition of Native Hawaiians holding the Mauna as sacred. And so the reason why this might be surprising is because the timeline that I just gave you started in 2009. And of course, that is not the timeline of this mountain. And so what I want to do is, rather than keep talking and explain this, I want to show you a short film. It's about 15 minutes long that documents the Native Hawaiian protests in 2019. This is sort of the second wave of protests that occurred to block the construction of the 30-meter telescopes. I'm going to switch over to that and play it, and we should be able to hear and see everything.
There's a lot of reasons we stand in opposition to the 30-meter telescope. Of course, the first reason is their construction on Mauna Kea is an act of desecration in and of itself. This is why conversations around whether or not they're paying enough money is moot, because the actual construction on that Mauna is desecration, and we will stand here until our death saying that no other construction is going to take place on that Mauna.
This mountain is held as conservation land. It is zoned as conservation land. Therefore, it's supposed to have the highest level of protections to protect that natural ecosystem as it's supposed to exist. Astronomical construction projects, development, roadways, parking lots, visitor centers, none of that should be in these spaces.
There are really serious environmental impacts we need to consider. The impact to our water, much of the water for this mokupuni is fed from that mauna. As the state and other agencies and organizations continue to propose and try to break ground on that mauna, they threaten that water, they threaten our native plants, our native animals.
It's really about a building and the inappropriate use of the summit of this mountain to house an 18-story building that has a 5-acre footprint and another 20 feet proposed to be built underground. And so the community, we're here with one common cause, and that's to stop trucks from going up the mountain to begin this newest project. There have been 13 telescopes built in all, and every one was going to be the last one. Our parents tried to fight it, we tried to fight it, and we continue to be steamrolled. And so we're not going to leave it for our children and our grandchildren to have to deal with. This is it. We're drawing the line in the sand, and we're not allowing any more development and no more desecration on the top of our sacred mountain.
To our people who have felt and who have said for many years, we need our rights back. We need to be respected as a people. We are indeed a living people with a living culture. And we can say that all we want. We've been saying it for years. And guess what? Kuli. They don't hear it. So maybe their vision is a little bit better than their hearing. And maybe we can demonstrate to them clearly what we mean by those words. This is about our right to exist, the way our kupuna existed. This is our right to be our kupuna. And so I ask my people, what kind of kupuna will you be? What kind of kupuna will I be? Like these kupuna, who are not moving. When we talk about our kupuna, we're not just talking about the end of their life and their time as a kupuna. We're talking about what they did in their va keiki, their va opio, their va makua. That's what makes them the kupuna that they are. So I ask again, what kind of kupuna are we gonna be? Now is the time. We have no other choice. We fight, we resist, we stand, or we disappear forever.
I cannot give him. No, I like you guys man carry me.
Aloha akue, aloha mai, e kuaina, iwi kukuna. Aloha nani e Kumamai kululu kalaba Ikua Kulalaba Ikua Ikua uki Ikua boy Ikua mau Amau kai ulu e uki e Ikua.
We had a meeting with some people, and at this meeting I told Kanuha, no, you're not getting arrested. You are not getting arrested. None of you are getting arrested. I'm going to get arrested. And my friend Gwen Kim going to get, and my other friend going to get arrested because you know what? My life almost pow. So now is my time to stand up for you folks. Because no more of our young ones. No more. No more. They have family, they have the future, they got their jobs. I'm already. I'm retired, I have my own hali. Enough. Let me do my part as a kanaka maoli. Stand for the Mauna now. Don't leave the Mauna.
Watching those kupuna get arrested, I will never forget it. I looked around and I saw people crying from their soul. Away. It's not a regular kind of cry. It's a cry where you cannot breathe because the people that you love, that stood for Kaho'olawe, that stood for Pohakuloa, that stood for the Mauna for the past 30 years. So many of our leaders that brought back our language, brought our hula back to the forefront, watching them zip-tied and put into vans. I will never forget that, ever.
I think it's important to understand the scale of the operation of the law enforcement that arrived that day. Law enforcement from the various agencies, police departments, the sheriffs, the Department of Land and Natural Resources, the Attorney General offices, all got together with police officers from 4 of the major islands, all amassed themselves to face off against our people.
So we were looking at the largest law enforcement operation in the history of Hawaii to come down on Hawaiians, short of the US military actually landing Navy and Marine officers to overthrow our government.
And our people did not blink. Our people refused to step away, and in fact, further entrenched ourselves in our culture and our dignity and our humanity to stand up for what is right.
One of the reasons we were so successful is because the police weren't prepared for the fact that every time they picked up a kupuna, another one sat down. But eventually, we were running out of kupuna. We needed to find a way to hold this stand and not just have them be arrested and then that was it, poho, they go through. So we started talking kind of in back circles saying, okay, when it gets to a critical moment, we are gonna call the manawahine to hold the line and the manawahine will take arrests next. And we thought we were gonna have, I don't know, 20, 30 people. And when it became clear we were gonna take the road and we started taking the road, we had over 100 women join us in multiple lines. And I don't think I've ever felt more sure of being exactly where I was supposed to be in my entire life. There was this overwhelming feeling that it didn't matter how many guns they had, it didn't matter how many batons they had, it didn't matter how many different toys and weapons they were gonna use against us, that we were far more powerful than they would ever be. And so all that humanity I felt that was stripped away from my kupuna in their arrest was like given, we like took it back. You know, we were really fortunate that we were so successful that no one else took arrest that day. The police, they didn't know how to deal with all of us.
That was the end of it for that day. There was a retreating of the officers that day. And from that moment on, we said, as we did in 2015, there would be no turning back for us.
The arrests themselves, what that did was really open up the earth in terms of the Hawaiian movement. We have thousands more Hawaiians now who are hungry for Hawaiian knowledge. And that is being also fed through the movement. It's being fed in a couple ways. One of the cool ways is through the establishment of the university up there. We have so many Hawaiians with all different kinds of knowledge that come up there. They teach classes, and whoever is just visiting get to partake in those classes. But we also have something that is even more meaningful, which is ceremony that is held 3 times a day on the access road. And it is a combination of chants, prayers, and hula. And this is a moment that is now accessible to the masses that used to be accessible only to Hawaiians who join a halau, maybe went to immersion school or a charter school, or enter the university. To be able to reconnect with chants, prayers, and practices of our kupuna that really facilitate coming into being Hawaiian and expressing through your voice and through your body your connections to this aina.
The biggest threat to the powers that be is a unified, organized, and educated Hawaiian people. And that's what you see going on today, is this resurgence of our knowledge as a people. I think that the state of Hawaii is very unprepared and very unwilling to understand what is going on in our community. Our people are rising. Our people no longer will accept being second-class citizens within our homeland. That our people demand our humanity and do whatever it takes through nonviolent direct action, including kapu aloha, to challenge all of those who exploit our lands, who divert our waters, and who reap benefits off of our oppression.
The reason that the state is coming so hard at us and our people are stepping up just as hard in Kapu Aloha is that we represent a massive threat to the settler society. We can literally huli turn everything upside down and say, no, we don't want to live like this anymore. We don't want to live lives completely dictated by capitalism and overdevelopment. We don't want to be told over and over that we're going to have entitlements because we're a part of the state of Hawaii, but then the state can do whatever they want to our aina. What's really happening here is that Hawaiians are saying, it's been enough. Understanding that a sovereign Hawaii, an independent Hawaii, a decolonial Hawaii is better for everyone.
The state of Hawaii has woken up a sleeping giant. Our people are now awake, and we can organize because of that. People try to portray this idea that Hawaiians can't be unified and Hawaiians can't get along. That's the furthest thing from the truth. As our kupuna would say, who could deny our intelligence, our abilities? For this is a path that has been commonly walked upon by our ancestors. We're not trying to do anything that we haven't done before. We're just trying to do it again. And this is just the very beginning. And if this is what we can do in the beginning, man, we can have a lot of fun imagining what we can do as we get closer to the end.
Together we rise.
So that film was made very shortly after these protests. And this was in July through December of 2019. And in December of 2019, the Hawaiian governor pulled back a lot of the police presence on the Mauna. And the National Science Foundation, along with all of the sort of partner institutions that were going to lead the construction of the 30-meter telescope, delayed that construction for the foreseeable future. And then, of course, in March of 2020, the COVID-19 pandemic halted all astronomical operations on the Mauna for a long time. And to this day, the construction of the 30-meter telescope has not begun. So these protests have thus far succeeded in their goal of preventing further construction on the Mauna. The operations of the other 13 observatories have continued. They were only shut down for a few days, and mostly You know, from the perspective of the native Hawaiians, that was an overreaction by the operators of those telescopes to this protest. They never intended to shut down all the astronomical observations on the Mauna, but those operations have continued. So that summarizes a big ethical question facing astronomy right now. And some of your readings were centered on this question of whether or not construction of the 30-meter telescope can continue, or can begin, I should say. Tasia asks, can the equipment be moved? So back to this picture. In late 2019, after these protests succeeded, the question of whether or not the Canary Islands could be used as an alternate location for the construction was proposed, but review by the Spanish authorities that have controlled the Canary Islands since colonization rejected the environmental permits that would be required to build it. So for similar reasons, this telescope can't be built right now in Mauna Kea or on the Canary Islands. So where this brings us is to some selections from readings that either you had for this lecture or are ancillary to those. And I want to highlight, because you read this paper by Chanda Prescott-Weinstein and all in 2020 about the issue of the Native Hawaiian sovereignty and how the operation of astronomical facilities should be considered in the future, especially when planning new sites for observatories. And in that paper, to commit the sin of reading off the screen here, I'll just say, that paper said, we recommend that astronomers engage in dialogue and negotiations in good faith, understanding that a deal may not be reachable, with a mandate to respect a no-deal outcome. And in a similar paper that was sort of written concurrently with that one, Kahanamoku et al. In 2020 wrote, we emphasize that development of large-scale astronomical instrumentation must be predicated on consensus from the local indigenous community about whether development is allowed on their homelands. These two papers were written and submitted to what's called the Decadal Survey. Every 10 years, the astronomy community, broadly defined, gets together, accepts submissions of papers for sort of the mission plan for the next 10 years. This is where we get proposals for things like the Hubble Space Telescope or the James Webb Space Telescope or the 30-meter telescope. So it's called Astro 2020, and you read a portion of it for today. And that portion was specifically mentioning this issue of building the 30-meter telescope on Mauna Kea. And I want you to take a look at this excerpt from that decadal survey, which sort of summarized and was as close as I could find to an equivalent statement to these two papers. These two papers were submitted to that decadal survey, and then the decadal survey is sort of edited from all of those submissions, and it draws ideas from all these different white papers to come up with this 600-page document that sort of outlines the future for astronomy in the next 10 years. And the closest equivalent statement that I could find to the two that are on the screen is this. The astronomy community adopts a higher standard than the bare minimum of legal compliance. Beyond the scientific benefits, astronomical activities would ideally add human value, educational, cultural, economic, respecting that different communities and cultures may ascribe value in different amounts or kinds, and may judge worth and worthiness through different lenses. A corollary is that the astronomy community must be willing to sometimes make difficult choices and to be open to alternative solutions that optimize more than the science alone. So what I want you to do here is to look for the difference between these statements on the left and sort of the consensus Astro 2020 statement on the right. And can you see something that is included in the statements on the left that does not appear in the statement on the right?
Well, on the left, they specifically highlight the respect of a no deal outcome. On the right here, I feel like what we're really doing is trying to sound ethical without actually creating a real ethical framework. We're kind of like, yeah, we're going to do better for sure. But sometimes we'll have to make difficult choices. So they're not really binding themselves to much here, except a little bit of lip service is kind of the way it reads to me.
Yeah, and I will say that this is a selection, right? You've got the full section of that report that you can read that's on the Blackboard. And I don't want to disparage the Astro 2020 report too much. There's a lot in there about how we transform astronomy by taking lessons from fields of study like archaeology. Archaeology has had a long history of transforming itself in recent years to try and be more sensitive to the to better honor the traditions of the native peoples that they might be, digging up the ancestors or the antecedents of. So the Astro 2020 report lays out a very bold vision for how we change how we do astronomy, but it stops short. And I really looked. This is as close as they come. It stops short of the possibility that we just don't build the telescope. And that really stood out to me. And I hope as you read these two things, that stood out to you, right? You read this one on the bottom left and this one on the right. So right now, the 30-meter telescope is not being built. But the Astro 2020 Decadal Survey has it as its number one ground-based priority for the next 10 years. And it'll take that long to build it. It'll take a very long time to build this observatory. Maybe not all 10 years, but it'll take a while. This is a standing issue in astronomy, and it is an ethical issue which scientists and astronomers are not always the best at dealing with and confronting. And so we'll have time in the Q&A afterwards to talk more about this. This has gone, I was afraid I was not going to have enough to talk about today, but this is actually going long. So what I want to do is we will address more of this ethical issue in just a few minutes here in the Q&A session. I want to look to the other side of our diagram now. We've now seen that even if you don't go to space, there are really serious ethical implications to observing space from the ground. And when I first thought about giving this talk, the bioethics of space exploration, the first thing I thought about was like Star Trek stuff, right? Like, oh man, like what about like the prime directive? Like, when we're this awesome futuristic spacefaring culture, how do we interact with other species? And how do we preserve the sort of natural evolution of life that we might find on other planets? And ironically, for something called the ethics of space exploration, I wanted to keep this talk a little more grounded in issues that face us today, like right now. And so while there are volumes to be written about those kind of ethical questions, the ethical questions of like, how do we preserve life if we find it on other planets? And what responsibility do we have to the native or to the existing systems of geology and biology that might exist on moons and planets in our own solar system? And how do we ethically observe and explore those without changing them? I want to keep us a little closer to home in our exploration of the go there side of things. And this will be quite brief here, because if we take another look at this diagram, it's pretty clear that if you want to do astronomy, you can't stay on Earth. You got to at least get up above the atmosphere if you want to look at the gamma rays and X-rays and ultraviolet radiation, or at the infrared light. And so we go to space. We build these enormously complicated and expensive observatories. The Hubble Space Telescope was launched inside of a space shuttle. But the James Webb Space Telescope, which I've kind of sort of tried to make to scale here, it's probably a little bit bigger than this from this perspective, but it's enormous. It's so big it doesn't fit in the top of a rocket. So how do you get it in space? Well, you got to fold it up. And so this thing folds up into a tiny little origami ball that you stuff into the top of a rocket and launch. And then it has to delicately unfold itself. It has to be so far from Earth to observe this infrared light that it's actually at a Lagrange point called L2, where if it ever breaks, it'll be completely inaccessible. We can't service it like we did the Hubble. So we have these observatories in space, and it's hard to get things into space, right? Here's a little table that astronaut Don Pettit made in a great blog post called The Tyranny of the Rocket Equation, which brings up the difficulty in transporting things into space. So if you look at these like modes of transportation, these vehicles, and you look at how much of them has to be made of fuel in order to move stuff around, right? A large container ship or a pickup truck or a car or even a locomotive is like only a few percent fuel. You know, the weight of the gas in the gas tank is not a very significant fraction of the car or the ship or the truck. But when you start talking about rockets, it's wild. The rocket has 85% fuel. It's mostly just propellant stuffed inside a very thin structure with a very expensive, or in the case of human lives, incalculably expensive and precious cargo at the top. And so one of the things you read today was a document that was presented as congressional testimony to the House Space and Technology Committee, specifically about gathering resources from the sort of Earth-Moon system. We'll talk more about this in the Q&A, but this sort of outlines the challenge of getting into space and utilizing the resources that might be there. So one of the things that you could do if you could get to the moon and you could figure out a way to process the water that we know exists, especially near the poles of the moon, is you could turn that pretty easily into propellant, into rocket fuel. Hydrogen and oxygen bound together in the form of water are this great life-giving substance, but you pull them apart and hydrogen is an incredibly powerful rocket fuel when you mix it with oxygen. So if you can find a way to pull those things apart, store them separately, and then mix them together in just the right way, you've got yourself a lunar gas station. And what this diagram shows is what's called the delta V to get around this Earth-Moon system. Delta V is sort of a measurement of how much your velocity has to change to get from one place to another. Rocket scientists don't talk a lot about distance because what you really care about is change in velocity. Because if you want to change your speed, you got to use propellant. And as we just saw, it's really hard to do that because if you need a large delta V, say to get from the Earth to the outer solar system, that means you need a lot of fuel. But fuel is heavy. So to get off the ground, you need fuel to lift that fuel. And then, of course, you need fuel to lift the fuel that you need to lift the fuel that you need to lift the payload. And it just keeps going, right? This is what is called the tyranny of the rocket equation. But if you could make that fuel in space, or at least out of the Earth's gravity well, then you might have yourself a business. And that is what this document was all about that you read for today. And so this gives you an idea of some of the sort of industrial activities that might occur at these different points in the solar system, or in especially the Earth-Moon system. This other figure shows you the sort of business case. So if you want to use Earth fuel on Earth, then you're going to pay, about, so this is $0.001,000 per kilogram, or about $1 per kilogram. Do the math right on that, I'm pretty sure. So it's pretty cheap if you want to get fuel on Earth and use fuel on Earth. But if you want to use fuel from Earth at these different locations, you can see these blue bars get real big real fast, right? If you want to use Earth fuel in low Earth orbit, that fuel, because you have to carry it up there, costs a lot more. GSO is geostationary orbit. That's the orbit that you want to put your communications satellites at. And that fuel is enormously expensive. The moon, like getting Earth fuel to the moon, is wild, $35,000 per kilogram. But if you could make that fuel on the moon, you get the green bars, right? Where fuel from the fuel from the moon used on the moon, well, now you're talking $500 per kilogram, which is not great, but it's certainly better than $35,000 per kilogram. And so once the green bar is below the blue bar, you have an opportunity to have a business. And that's what that document was kind of all about. So a quote from that document: "It turns out that if you can buy propellant in orbit for less than it costs to ship it there from Earth, the business case can close. At these prices, the cost of any activity beyond low Earth orbit becomes dramatically reduced. For example, the cost to deliver mass to the surface of the moon will be reduced by a factor of 3. The cost of a Mars mission will be similarly reduced." So you can see that the water on the moon is an immensely valuable resource. Strategically, we should view the poles of the moon as the next Persian Gulf. The ethical red lights are rotating right now. So one of the documents that I asked you to read for today was a document about the concept of planetary protection, about how we should view space resources. And I want to kind of finish with a quote from that. "Many people consider it inevitable that resource extraction will be a fundamental part of space exploration, if not the reason for doing it at all. However, it's worth questioning whether our current mode of extractive capitalism is something we should take with us when interacting with other worlds. Enabling those with wealth to privately engage in space exploration efforts could exacerbate already extreme wealth inequality in the immediate future." And speaking of space exploration, there's a company called SpaceX, and the X stands for exploration. And this company has done some amazing things, right? Created the first really reusable rockets and reduced the costs of exploring space by orders of magnitude, by being able to recover the parts of a rocket you would normally have to throw into the ocean. Because again, the less stuff you have to take to space, the better. So once this thing, which is just fuel tanks, is empty, dump it off the back of the rocket and throw it into the sea, because you don't want to lift it any higher than you have to. SpaceX is one of the companies, along with Boeing, that has been contracted by NASA in what's called the Commercial Crew Program. SpaceX has developed a crew capsule that has successfully ferried passengers to the International Space Station. And so since the cancellation of the Space Shuttle program, this is now a return to flight for the United States. This is now regaining the ability to bring astronauts to space from the territory of the United States. And it has advantages over the Space Shuttle. This rocket has an escape mechanism. The capsule itself can detach from the top of the rocket if anything goes wrong during launch and safely bring astronauts back to Earth. That is something that the space shuttle very tragically could not do. And one of the projects that SpaceX is working on is called Starlink. And Starlink is a technology that deploys satellites into orbit to bring internet access down to Earth. And that access is something you could do now, right? If any of y'all live out in the sticks, you might have to have something like HughesNet, something like satellite internet service. The existing satellite internet service is based upon geostationary satellites. So geostationary satellites are in a very high orbit around the Earth, so high that they orbit once around their orbit in exactly the amount of time it takes the Earth to turn once in its spin. And so what that means is they appear to be stationary. And that's a great place to put a communications satellite, because it means that it's essentially hovering over the planet and it sees the whole, one side of the planet all at once. So if you're trying to bounce signals back and forth, it's great because the target in the sky is stationary. In fact, this is a picture taken from a geostationary satellite this morning as the sun rose over Arkansas and that storm from last night went off to the west or to the east. Now, Starlink is different. Starlink is not deploying satellites into geostationary orbit because that's really hard. It's really hard to get a lot of mass into geostationary orbit because it's so high. It's a lot easier to put stuff into low orbits. The problem with low orbits is they don't do this. They don't hover. They zip really quickly. And so the solution is lots of satellites. If you can deploy thousands of communication satellites that swarm around the Earth on these predefined orbits, then your satellite dish on your house can always see at least one or two or three of them in the air at the same time over your house as they sort of zip from horizon to horizon. And as long as there's a couple, you can send messages up. And as you can communicate up and down with the satellite, you can see that satellite can pass that message through the web with satellite-to-satellite laser beams and then bounce that back down to the Earth to go load the website you wanted to load. But this requires thousands of satellites. And this poses its own ethical problem. We talked about space junk and space trash yesterday. These things are at very low orbits. Now, the advantage of that is there's not a lot of stuff down there for them to run into, but it's not empty. There have already been thousands of maneuvers that have had to occur in space in order for these satellites to avoid hitting other space debris. And in one case, for the Chinese space station to move to avoid a potential collision with a Starlink satellite. For ground-based astronomy, this also presents problems. Back to photography for a second. Remember, you have to take nice long exposures if you want to gather light from space. Well, if you are exposing your image for a long time and a satellite goes by, that leaves a streak through your image. And if a dozen satellites go by, that leaves a lot of streaks through your image. So in that Astro 2020 report further on down, it says the impact of mega constellations is noticeable for wide field imaging at optical wavelengths. It'll become more significant in the future and will potentially severe for some programs, especially from satellites in orbits above 600 kilometers, which these aren't. Unless their effects are mitigated, facilities especially impacted would include the Vera Rubin Observatory. Scientifically, the greatest impact is on searches for near-Earth objects, i.e., those killer asteroids that we want to keep an eye out for. In the radio, this is also a problem because those satellites have to communicate up and down with each other and with the ground, that creates a lot of radio noise. So over here on the left, we've got a nice clean radio picture. And over here on the right is what happens when you pop a communications satellite, not even inside the frame, but several degrees off, or several arc seconds rather, off the frame. Just the bleed over in the radio communication bands completely swamps the signal you're trying to gather. And so for radio astronomy, this is particularly hard because instead of geostationary satellites in nice predictable orbits that you can just not look at, these mega constellations of really low Earth orbit satellites and their radio signals create a huge problem for radio frequency interference. All right, so that's my time. And I want to make sure that we've got some opportunity to answer just a few of the questions that we have in the chat that have been going by here. Does exhaust from space shuttles affect the environment any? I mean, yeah, if you want to talk about carbon emissions, anytime you burn a hydrocarbon, the two things you always get out are carbon dioxide and water vapor. So all that stuff you see coming out the bottom of a rocket is carbon dioxide and water vapor. And carbon dioxide is a greenhouse gas. So yes, they affect the environment. As a proportion of human exhausts, it's minuscule, but that's today. If you want to start building industries in space, then you got a lot. How are they allowed to launch so many if it can be so harmful? Well, the thing we didn't get to talk about very much is space law. And you had a document to read about space law. The truth is that space law is hard. You have an ambiguous duty to preserve astronomical observations when you put something into space. All you really got to do is make the FCC happy that you're not going to interfere with communications, and make the FAA happy that you're not going to kill anybody, and you can get approvals to put things in space. In the future, as space travel becomes more popular, do you have an idea for solutions for the carbon emissions that space travel makes? Nope. I don't. Your only two options are stop doing it, stop making emissions, or find a way to get them out of the air and put them back in the ground, which is very hard. Let's see. I think that's most of the ones that I saw scroll by. John, Linda, I'll turn it back over to y'all for the end here.
All right. Space Trash Lusk, our big woo! Huzzah! Huzzah! That was awesome. And multi-ranging, don't you think, Click?
That went all around the world, Clack.
Wow. Yeah. The readings on space law were amazing. I had no idea, class. In fact, boy, physics is hot. Physics is sexy. That's a takeaway. What do you think? Physics is sexy. We can help with the titles because we're the humanists, but boy, that's amazing stuff. Really fantastic. So we're going to take a 15-minute break, which would put us at
11:50.
11:50. Why don't we come back at 11:50 and tangle some more with Professor Jeremy Lusk. That was amazing. Woo!
Well, thank you so much, folks. I really enjoyed it.
All right,
Wonderful.
we'll see you at 11:50.